Our substitution elimination were typically alkyl halides. They're really straightforward. Halogens are awesome for substitution elimination because they can only do one thing. They can only leave the structure. Okay? They may have electrons, but they can't share those electrons with anything outside the structure because they really should only form one bond. Okay? We do have other functional groups or other atoms that could act as leaving groups. Oxygen could potentially act as a leaving group because it is very electronegative, like our halogens. However, oxygen adds an extra little wrinkle to this. Okay? Those lone pairs are donatable. So because it has lone pairs, it can act as a nucleophile. Okay? Or just nuke. Because it is electronegative, it could potentially act as a leaving group. So our alcohols are now significantly more challenging potentially to work with because depending on our conditions, we could have that acting as a leaving group or as a nucleophile. So we have to be a little bit more careful with those functional groups. Okay? And that's why it can be bad, because if I want to do just a straight substitution, I could potentially run into the issue of the oxygen acting as a leaving group instead of as a nucleophile. Okay? So I have to be careful and consider the conditions that I'm running in. Okay? So one of the things that we tend to do is that if we have an alcohol, one of the first synthetic things we would do is get rid of it. Turn it into something that limits that activity. So instead of using an alcohol functional group, I convert it to a halide. Now in the halide form, it can only act as a leaving group. Okay? How do we get to the halide form? Well, OH is a bad leaving group, so you add a strong acid. The strong acid protonates the alcohol, making it water, which is now a phenomenal leaving group, and we have strong nucleophiles that could potentially come in. Okay? Bromide, iodide, and chloride. Okay? That chemistry should be apparent because what you should be looking at is the reactivity in each of these. Not looking at thinking about the reagents and what should the product be, but think about the reactivity. All of these things are strong acids. Okay? So neutralize the strong acid. Give it electrons. Where are their electrons? The oxygen. All of these end up going through and generating an intermediate structure with water as a phenomenal leaving group. That says plus. We're now addressing that oxygen is acting as a leaving group, not as a nucleophile or base. Okay, so if we focus on the chemistry, we don't have to memorize the result. We can see what things are reactive and try and predict through it. Okay, you will have to do that on the ACS. Okay? One of the things that may pop up as we go through and do that kind of process, though, is you may see extra reagents. For instance, with HCl, you see zinc chloride. Why is zinc chloride showing up, but we don't see anything extra for HI or HBr? Oh, it's doing the exact same chemistry. Why would that matter?
Maybe because chloride will precipitate.
It's a catalyst. I don't want the chloride to precipitate because I want the chloride to connect to the carbon. If the chloride precipitates, it can't react. So what is the difference between the chloride, iodide, and bromide? Size. What are they acting as?
Leaving groups.
They're not acting as leaving groups in this case. They're acting as nucleophiles. Why might the chloride need something extra?
Is it the worst nucleophile?
It's the worst nucleophile. Iodide and bromide are both better nucleophiles, so I don't need something extra. Okay? If you see something extra, you don't necessarily have to use it. Would you still recognize that HCl is a strong acid? Would you still protonate the oxygen? Would that still be a good leaving group? Would chloride still be a decent nucleophile in your opinion? Yeah. Do I need to evaluate zinc chloride? No. Okay. So just because it's there doesn't mean you have to zero in and focus on it. Okay. Work with what you have and worry about the rest later. Okay. What happens on the flip side? If we take sulfuric acid, that's now a strong acid that will protonate. Okay. The interesting thing in this feature, though, is it's saying dilute. Okay, so not only is it dilute, not a lot of acid, that means not all of the alcohol becomes a good leaving group. Some of it doesn't. Because remember, we're running this at billions and billions of molecules. Okay. Do I have a nucleophile in the sulfate?
No.
It may be negative, but the resonance within the sulfate makes that a horrible nucleophile. Well, then what's left to act as a nucleophile?
Another one of the substrate.
Okay. If I have billions, I'm not going to do billions, I'm going to say 2. Wasn't supposed to be that funny. Actually, I don't think it was supposed to be a joke. Sorry. If I have 2, one of them gets protonated. What happens to the other one? Well, it doesn't. What does the other one still have? Lone pairs that could act as a nucleophile, where the other one has a leaving group. What happens? We can then connect those 2 carbon structures through what functional group?
Turn ether.
It's now an ether. Okay. Why would I do that? What happened to the reactivity of the oxygen now once I've made it an ether? Do I have the hydrogen anymore? No. Do I still have the lone pairs?
Yeah.
Yeah, but where are those lone pairs now hidden behind?
2 big.
2 large carbon structures. I've reduced the nucleophilicity of that oxygen. I've changed its chemistry. Okay. What happens if I switch up to concentrated sulfuric acid now? Well, if it's concentrated, now I don't have any leftover alcohol to act as nucleophiles. So where do I get electrons to stabilize that structure? I have to find it internally, and I end up doing an elimination, okay, forming the pi bond. So recognizing the patterns in your chemistry can help you get through these. Okay. The next one, alternate activations, as I'd like to call it. Don't stress too much on. They might pop up, they might not. These all are second semester official. Okay. What's happening with these? We're starting with an alcohol. Are we reacting it with a strong acid? No. Okay. So no strong acid, what's going to happen? Well, the alcohol still has this weird potential chemistry. So I might want to convert it to something else. These reagents will convert the alcohol to some other functional group without going through an acid intermediate. Why might that be important? What do acids tend to do to things? Protonate, ultimately react with. If I look at a complex organic molecule, there's probably not one site that's reactive. There's probably 20 or 30. If one of those happens to be acid active, I can't run the previous slide. I would need a new functional group or a new reaction to avoid that conflicting chemistry. Okay? So we have a variety of reagents that will allow for these kind of shifts. Recognizing the chemistry behind these becomes significantly more difficult because you're typically not given structures. Let's take a look at SOCl2. What do you see when you look at that structure? What's that?
Resonance.
Resonance. Okay. Lone pair electrons, or sorry, the pi bond could go up to the oxygen. Why would they go to the oxygen, not the sulfur? It's more electronegative, which means what happened to the sulfur? Became positive. What things act as positives? Electrophiles. What did we say the oxygen could act as? A nucleophile. The oxygen can attack the sulfur. We would exceed the amount of electrons on the sulfur. It kicks out a chloride. Okay. The next step is that we've now converted that oxygen into a great leaving group, and the chloride that was just kicked out can now act as a nucleophile back on our carbon. Okay. So when we talk about second semester being lots of reagents and memorizing reagents, this is ultimately what you're looking at. Okay. We take a big, massive step away from structures that you're familiar with or that are relatively simple. I know those are all acids. If they act as acids, this is what happens. To now looking at structures that have these complex formulas, and you're expected to either memorize the reagents or use what we learned back in Unit 1 to draw those Lewis structures. With the Lewis structures, you can then come up with predictions of the chemistry. Okay? So look for patterns within your multiple choice and try and appropriately shift through them as best you can. Kind of make sense? Okay. Ether synthesis. And we actually just looked at one. The whole point of making an ether is to do what? That oxygen needs to have another carbon on it. Okay, so it's not a nucleophile. Okay, which is going to be a couple things. I'm going to need a good leaving group because I've got another carbon coming in. Okay? That carbon or the oxygen, the new one, has to be positive and negative. That's how these things hook up. So I'm going to need a good leaving group and I'm going to need a good nucleophile. Okay? So depending on which I decide to focus on, I'm going to get a slightly different reaction or reaction conditions behind those. Okay? The big one that usually stands out is the second option. I add a strong base to the alcohol. How do I neutralize the base? With an acid, I would need an acidic hydrogen. What's in the alcohol functional group? An acidic hydrogen. Okay, for those of you saying, oh, but a strong base means elimination. That is a good first semester thought process. Does it work with alcohols? Okay. Strong base should remove a hydrogen, right? Do the elimination. The hydrogen that the strong base removes must be the most acidic. Which hydrogen is more acidic? The one connected to the carbon or the one connected to the oxygen? The oxygen. So I don't end up doing the elimination, and instead I do a straight acid-base reaction. What does that put on the oxygen? That's supposed to be a double-headed arrow. A negative charge, meaning what do I now have? A good nucleophile. In the second step, what can happen? I need to bring in an electrophile. Okay? So it's just trying to follow the chemistry through. Okay? For the type of ether synthesis where we make a good nucleophile, so as shown here, it has been named after the original discoverer. Okay? Of course. Okay? Why? I don't know why. I literally don't know why for this one. That makes no sense to me. Okay? We're looking at insanely basic chemistry behind that. There's nothing particularly tricky or like, ooh, that shouldn't happen. Okay? Markovnikov, fine. You didn't know what electrons were. Zaitsev, fine. You didn't know what electrons were. Williamson, you're following everything about basic chemistry. There's nothing fancy there. Okay? But it is sometimes referred to as a Williamson ether synthesis. Okay? So you just kind of have to watch out for that terminology. Okay? So in our Williamson ether, we remove the hydrogen from our alcohol, make an extremely strong nucleophile. That nucleophile can attack an electrophile, and we get our ether. Okay? This would move us into kind of the next realm or topic, which is kind of convenient for being the last class. Synthesis. Okay? A lot of what happens in second semester is we say, here's a product. You're like, oh, that's nice. But now we say, make it. Okay? Usually there's extra pieces of information stacked on top of that. Like you can only use pieces or you have to stop when you only have so many carbons in your starting materials. Okay? So you have to pay attention to those extra rules. The other thing you've got to watch out for is where should you start making it? Okay? We'll find the most electronegative element in your product. Why? It's probably going to take electrons. Okay, which would mean it's a partial negative, which means the other one is partially positive. If we split that bond, can I make that oxygen negative and the other atom positive? If I have the reagents to do so, guess what? That's now my starting material. I'm done. Okay? If there's multiple different sites that are polar like that, I have to address each of those sites. Okay? Conveniently here, it's relatively straightforward. Okay? There's only one electronegative site. Which one do you guys want to look at, left or right? Left. Left it is. Okay, so when we look at the leftmost structure, I have that electronegative oxygen. Right? So that is pulling electron density from either of those carbons. Which one of those bonds do I want to make? Okay, so really it's two options. We've talked about it a couple times, floated it out there. Really, organic chemistry is just 50-50. Here's another 50-50 split. If you don't know, what should you do? Do them both. So let's split it. For number one, what happens? If I split that, I would be forming a positive charge here, and then I'd have my negative oxygen still connected to that other carbon. Yeah? Okay. Can I have that as starting materials? That becomes a harder question. They're charged? No. So I'd have to somehow neutralize them. Okay. How could I neutralize the positive carbon? Put a chlorine on it. Why'd you suggest chlorine? I'm going to do bromine. I want something that acts as a good leaving group, that would leave behind a partial positive, okay, or a formal positive. Okay, how could I make the oxygen not showing a formal negative? I could go through and protonate it. Okay, that's one option. What kind of reaction would I be running? So now I've got potential reactants. I now want to test this theory. What reaction am I going to run to go from these starting materials up to my product? I'm going to be doing a substitution reaction. You said SN1. Why SN1? We look at our substrate. The substrate is tertiary. The substrate chemistry, being tertiary, suggests SN1. The other thing you should evaluate, the strength of the nucleophile. Is that nucleophile strong or weak? It is weak, which also suggests SN1. What is a massive complication of SN1 mechanisms? They always do eliminations. I want to make that starting material to the best efficiency possible. Is an SN1 mechanism going to be a good option? No, probably not, because it's probably also going to do an elimination, and I don't want that competing. So an SN1 is a bad idea. How can I make sure this doesn't do SN1? It does SN2.
Make it a good nucleophile?
I could now use a strong nucleophile. Remember we said we can't have that charge showing. How can I make sure I have a negative oxygen without the charge showing? Put a metal next to it. Now the charge has been hidden in the structure. It's still there. Okay. So I have a strong nucleophile. Awesome. That suggests SN2. What's my substrate? I didn't touch the substrate, so it's still tertiary. Does tertiary favor SN2? No. So a strong nucleophile is also a strong base. Why does that become problematic? Tertiary substrates favor E2. This reaction now isn't going to favor the SN2, it's going to favor the E2. What does it mean about splitting that first bond? That was a crap decision. There's my 50-50 coin toss, particularly on a multiple choice answer. More than likely they gave you this one first. Okay? Because you look at it and go, oh, that's a nice split, that has all the pieces, that's got to be my answer, I'm going to move on. Okay? You have to not just guess at the possible answer, but test the answer. Does it work? No, it doesn't. So that means I've got to be doing the split the other direction. Okay, method 2. What happens when I look at method 2? Okay, well, I'd have my oxygen connected out to those carbons, and then I would have what's left over. Okay, I'm going to have to write the CH3 because I can't just show a point. That wouldn't be very helpful. Okay, what charge would the oxygen likely be? Negative. The carbon? Positive. Okay. What kind of reaction are we trying to run? Starts with an S. Substitution. Okay. What mechanisms should I be considering? SN1 and SN2. Okay. For it to run SN1, I would need a weak nucleophile. So I could put a hydrogen on there, but I'm going to hold off on drawing the hydrogen because it's ultimately a bad idea. Because if we look at the substrate, what substrate do I have? A zeroary. Can I do a zeroary substrate in SN1? No. Okay, I will never form that carbocation, which means SN1 isn't an option for me. Okay? I have to have a strong nucleophile. It has to run SN2. Okay? How can I get rid of those charges now to better account for that? The negative can't be shown as a negative. What does it need to be? A metal. Okay? I picked potassium on the first one because I thought KO would be funny. Yeah. Na, sodium, also common. Just as easily drop that in there. I can't form a positive or a zeroary carbocation. So how can I make sure that that carbon is still partially positive? Attach it to a more electronegative thing. Could I attach it to oxygen? Do an OH. What's the problem with OH? Not a good leaving group, and it has an acidic hydrogen. What could my nucleophilic oxygen act as, that red one? A nucleophile or a base. So adding an OH here is my potential. Does generate that positive, but it also brings in more chemistry. I don't want to bring in more chemistry. What functional group could I add that, oh, please reconnect. What functional group could I add that doesn't bring in more chemistry? A halogen. Chlorine works. I just like bromine better. Okay? Now what happens? We'd be running an SN2 type reaction. Anybody have a problem with calling my oxygen here a nucleophile?
Bulky?
It is bulky, which would suggest base, which would suggest elimination. Can I do an elimination? No, because there's literally nothing to eliminate. I have to have a beta position. I don't. This is now the best sequence I could possibly run. Okay? All of those thought processes have to happen with synthesis. It takes time and practice to get through. When you move into, if you move into second semester, that's what you'll be constantly thinking about. Okay? So synthesis is a perfect example of trying to think about everything we've learned and put it all into one gory question that you're still supposed to answer in less than 2 minutes. That we just spent like 20 on. Okay? So epoxides. We formed epoxides with the MCPBA, right? Everybody remember that? Vaguely at least? Epoxides are synthetically useful. Everybody asks, oh, I want to know the real world application. Though those pictures are natural epoxides, so those are things that show up in different forms in biology as intermediates that would then get reacted out to form something else biological. I don't know, I'm not a biologist. Okay. I know number 2 looks kind of familiar. Number 2 looks like a steroid, one of them potentially. Okay. So what happens with our epoxides that we now need to worry about? Okay. So what we've got shown up at the top are now 2 possible epoxides. Okay. They're identical epoxides, no difference between these. Okay. But notice I'm showing the wedges and dashes in different locations, right? Why? When we look at an epoxide, we have a ring, which we could show, I can't, well, there we go, there's my ring. Just pretend those are connected. Right? Those are sp3 atoms, which means I would also have things coming in and out of the plane from those positions. Everybody see that? So in this case, I'm showing the substituents. I'm showing the epoxide as the primary functional group because everything's in the same plane. It's in the plane of my paper. Okay, and the substituents would be coming out. Okay? I could also draw it this way, in a Hayworth-like projection, okay, where the ring is now coming in and out of the plane at you, and the substituents are now up and down. That's what we're trying to show in the top case. That gets a little bit weird. We can't officially do that perfectly because it's a tetrahedral carbon. I can only have two solid lines. Okay? But they're both representing the same structure. Okay? I personally find it easier to deal with the epoxide in the plane of the paper, so that's where I'm going to keep my focus. Under basic or neutral conditions, I'm going to have a strong nucleophile. Okay, how would I know a strong nucleophile would be present in basic conditions? What about the charge? Yes. Bases are electron donors, meaning the solution would be negative. What is a nucleophile? Negative. So under basic conditions, I would expect strong nucleophiles. Okay? That strong nucleophile is going to seek out a positive. Where is there a positive in my epoxide structure? Okay. The oxygen is polarizing those bonds, making both of those carbons partially positive. Okay. So I now have two possible options. So we're kind of preluding second semester here. Where's that negative charge going to attack? Which positive? Okay. I hear a suggestion that it should attack the most substituted. Why would you suggest that? It would be a more stable carbocation. That's a phenomenal idea. Is that a carbocation? No. Will we form the carbocation? No. Okay. What's the argument for the other position? It is less sterically hindered. Okay. Both cases, these have to do a backside attack, a backside of that carbon-oxygen bond. So in both cases, we're SN2-like. Okay. But if we choose the red path, we're also SN1-like, because we're attacking the more substituted. If we choose the purple path, we're fully SN2-like. Okay? So the substrate's confusing as all crap. So what else should we evaluate? There were three things that you're told to evaluate when looking at substitution reactions. Substrate was one. We just said that's confusing. Starts with an N. The nucleophile. What kind of nucleophile do we have? Strong. A strong nucleophile favors which mechanism? SN2. Guess where our nucleophile attacks? It attacks the least substituted. Right? And the purple reaction ends up becoming valid. We break open our structure. Right? Not particularly convenient here. So we'll talk about that in a second. Notice the nucleophile comes in from the back side. Our oxygen is now on the opposite side. If we think about where the ring was, the oxygen and the nucleophile are on opposite sides of the structure. We've done effectively an anti-addition. Okay? Anybody have any problems with the structure shown? So I'll tell you I do. Why? Yeah, that's usually a good question. Because it's me. I always have problems with things that are shown. Where the hell did the hydrogen come from, right? The electrons come out, go to the oxygen. What would we expect to see as a product? A negative oxygen. Okay, so it really should be a negative oxygen here. Okay, well, where would the hydrogen have to come from then? From an acid. Can I have an acid present in this reaction? I'm under basic conditions. I can't have an acid. So where do I get the hydrogen from? Step 2. Add acid. So if we're looking at the epoxide reaction under basic conditions, you will almost always see it as 2 steps. Because to protonate that oxygen, you need to add an acid, and under basic conditions, we don't have that. So we have to run a second step. Make sense? Ish? Okay, let's make it worse. What happens if we're now under acidic conditions? If we're under acidic conditions, what's the most reactive thing present? No. Lone pairs would not be a good option for being reactive if we're under acidic conditions, because under acidic conditions, what charge am I? Positive. So addressing lone pairs that are negative in acidic conditions, I don't appreciate. And not in like that way. What's likely to be the most reactive thing under acidic conditions? H+. How do I neutralize that H+? I don't have an OH. If I had an OH, it wouldn't be acidic conditions. With electrons. Now where are my electrons? The lone pairs. So it's not that lone pairs aren't involved, but it's trying to find the focus of where the chemistry is. Find your chemistry first, address that reactive site. Once that is addressed, then you can move forward. Okay, so the lone pairs on our oxygen should now go through an attack. RH+. What's the result? Okay, we would now have hydrogen connected, whoops, ignore the mirror, man, curtain, one of those things. Wizard of Oz reference. Watch that, it's a good movie. And musical, I think. Positive charge on our oxygen, right? Is that stable? No, that's not stable. Okay, what is it trying to do? Get some electrons. Where could it get them from?
One of the sigma bonds.
From any one of the sigma bonds that are connected to that oxygen. So I could pull them from the red hydrogen, the blue carbon, or the orange carbon. Okay. To do so, I would be forming a charge on that carbon, okay, or on the hydrogen. The hydrogen takes me backwards, so let's ignore the red one. We're looking at the blue or the orange. Okay? So both of those would be partially positive, right? So what would they need to react with? I don't quite accept something that is negative. I would need to react them with a nucleophile. And in particular, what kind of nucleophile should it be? Can I have a strong nucleophile under acidic conditions? No, it has to be a weak nucleophile. Notice the nucleophile I've shown does not have a charge. Okay? The nucleophile needs to be weak here because otherwise I wouldn't have the hydrogen on there. So now where does the nucleophile attack? Okay? I got blue or orange. But it just attacked the blue. Why shouldn't it still attack the blue? The substrate's confusing. Ignore the substrate, move to the nucleophile. What type of nucleophile do we have? Weak. The weak nucleophile should favor which type of mechanism? SN1. Which substrate position is more SN1-like? The orange. And we end up seeing the epoxide react in a different fashion. Okay? So if we focus on the chemistry of our structures, we can predict where those show up. It's still going to be anti, but notice now the nucleophile and the alcohol are located on different positions. You'll also notice for this one, we don't have step 1 and step 2. This is all done in one fell swoop, one solution. Why? The previous case, I needed a strong nucleophile. I couldn't have an acid present to protonate. In this case, I needed a weak nucleophile. Perfectly all right to have an acid present because it's going to be a weak nucleophile. So recognizing the chemistry in our structures can help out. So when looking at anything that you think is substitution elimination, you should be evaluating the strength of your nucleophile and your substrate. If you are forced to, you can then move to the solvent. Okay? But those three things need to get evaluated immediately because that will help dictate which mechanism, and then you can worry about the complications of each of those mechanisms. Make sense? Enough? Here's our big summary. for our epoxides. MCPBA is the big one that you typically see. If they're being obnoxious, what they will go through and do is hide the fact that it's MCPBA in one of a couple different ways. The first way is they'll call it RCO3H. Okay? That is a peroxy acid. That is the PA of MCPBA. Or they'll go through and actually be somewhat nicer and they'll show you the structure. Okay. There's our 3 oxygens. The peroxy is right here. Okay. Any of those means you're going through to form the epoxide. The epoxide could then potentially open up its ring. Why would it want to open up that ring? It's not stable because ring strain, okay, or bond angle strain. One of those named strains, I don't remember which one it is, but it's not happy. Okay, we want 109.5 and we're at 60. Okay? After that, you've got to evaluate basic neutral conditions or acidic conditions. Okay? I'm setting this up so that you could theoretically memorize if you wanted. Okay? But we walked through it looking at the chemistry of each of those things. That's what helps you predict these things. Okay? And again, it's literally a 50-50 split, okay? All the way through that. If you make any wrong 50-50 split, you end up with the wrong answer. Okay? Which gets us to our last, hallelujah, chapter, our radical chemistry. There's a significant amount of content within the radical chapter. You are more than welcome to go through and read it. And Cardi, they're going to go into a lot more detail than I will touch on here, ultimately because radicals have very limited synthetic use. Okay, so we'll see the summary slide in a little bit on what you'd be asked as far as synthesis goes or reactions. Okay? But for the most part, the reason we have radicals is because alkanes aren't reactive and alkenes are minimally reactive. They do have the pi bond that does make them reactive, but radicals can now mess with that chemistry. So how do you know you're looking at a radical? Well, it's an unpaired electron. So we've got several cases for radicals shown along the right-hand side. Believe it or not, oxygen, okay, this is just O2, is actually a radical. I'm like, really? I breathe in oxygen? People are talking about free radicals and being dangerous, and I die if I have free radicals, and literally oxygen is a radical. Yes. Okay? That is actually why we survive, because oxygen is a radical. If it wasn't, we can't process the oxygen and we don't live. Okay? So it needs to be a radical. Those varying radical states can get hidden behind other chemistry. For instance, the O2 isn't particularly obvious as a radical. Okay? Why might it be a radical? What can you tell me about oxygen and oxygen? They're both electronegative. So what are they doing to the electrons in their bonds? They're both equally pulling on those electrons. So what likely happens is that each oxygen removes one electron from the pi bond. Why would it pull it from the pi bond? The pi bond's the highest energy, and we can generate an oxygen radical. Okay? It's that observation that explains why we exist. It also helps to explain its, magnetism. If you take liquid oxygen, they showed you that video. It's kind of neat. It's actually magnetic. Okay. The other ones, we've got another oxygen radical up here, bromine radical, carbon radical. Carbon radicals are synthetic one because it's OChem. We want carbon radicals. Bromine radicals. Actually, let's take a step back. Okay, what makes a radical reactive? What does it act most like? It's going to act most like a carbocation because it has an unpaired electron. So when we're looking at radicals, you need to be treating them like carbocations. So if you're asked to do a radical reaction, find a place that's a good carbocation, make that your radical. Do what you got to do, make it a radical. What do we got to do? You're removing hydrogen. Okay? That's tricky to do. That's why we have to do radical reactions. So all of the radicals we end up forming all have varying stabilities, and for the most part, that stability is dictated based on the substitution of the radical, right? Resonance effects and the such. So that's why the bromine radical is decent, because it is big. It can stabilize that lack of an electron better than most other atoms, okay? Oxygen being electronegative just makes it super nasty and radical. Same deal with the top one, okay? We get the potential for electrons moving around. The more we can move electrons, the more we can potentially stabilize those. Okay? So as far as our radical reactions, they are not fun mechanisms to deal with. I will show hopefully just one. Maybe I'll show them both. Okay? They break down ultimately into three categories. The initiation. Okay? The whole point of starting a radical reaction would be to get a radical. So you need to find a bond that would split what is known as homolytically. Homolytically meaning the electrons going back to their parents. Okay? So this first one works as a homolytic cleavage. Why? Oxygen-oxygen bonds. That's not a happy bond. That will split where each of those oxygens grabs a single electron and generate two radical species. Okay? The key chemistry in that one was the oxygen bonded to the oxygen. Both those oxygens were connected to some carbon structure. What's our symbol for carbon structures? R. Made reference to it a couple times, I think, in class. This is our ROR. If you see ROR, or our RUT-RO, or RO-RO, okay, then you can get scared. You need Scooby-Doo. You got to do radicals. That wasn't that bad. You don't have to roll your eyes at that one. I don't know. Why was I calling you out? Oh. I had flair. Bromine. Okay. Bromine is now two electronegative elements again. Okay. Bromine's bond is a little bit stronger than the oxygen-oxygen bond. In the case of the oxygen-oxygen, I just need heat to break it. Give it a little bit of heat, it breaks apart. Bromine, not as easy to break apart, and I need to hit it with light. Okay? And it is typically ultraviolet light, so you may see it written as H nu, which if you don't remember all the way back in general chemistry, H nu is the energy from the electromagnetic spectrum. So it's just saying hit with light. You may also see it written as light. Okay. You may also see it referenced as UV. UV being ultraviolet light. Okay. So all of those are saying the same thing. We're causing the bromine to split into the radicals. So we're breaking a sigma bond, okay, to make our radical. Okay. So if you look at a reaction and on the left-hand side there's no radicals, on the right-hand side there are radicals. Right? That's an initiation. After we've initiated, that radical now needs to stabilize. And it needs to stabilize by finding a pair of, or a single electron from somewhere else in the solution. Okay? So that now depends what your reagents are in the solution. Okay? So in this top case, if we're looking at an alkane, okay, the odds the bromine encounters the alkane structure, not too bad. That's actually pretty reasonable. What's the most likely thing in that alkane that the bromine would interact with? Okay, as a hint, there's only two atoms that it could possibly interact with. One begins with C and one begins with H. That would be carbon and hydrogen, yes. Okay. Why would it react preferentially with the hydrogen instead of the carbon? Radicals are insanely reactive. Right? Is it going to spend its time to get by the outside of the structure to get to the inside? No. So it reacts with the surface. It's going to react with hydrogens. Right? Are the hydrogens all the same on that structure? No. Both of them are possible, so both of them could generate radicals. Which of those radicals is more stable? Okay? The first one, because remember we treat these like cations, I would have a secondary cation versus primary cation. When we're looking at our radical reactions for synthetic uses, when we're using bromine, we don't form the primary. It doesn't happen. We only get the secondary. Okay? Our radical could potentially now see something else in solution, like more bromine. So we could go through and do a radical reaction with the bromine to neutralize the carbon radical, but at the same time it produces another radical. Okay? That radical could potentially get reacted further on down the chain. So in these cases what we're looking at is propagation steps. We start with a radical, we end with a radical. It doesn't stop, it just continues to go. This is one of the reasons why radical reactions are dangerous, and free radicals in the body can be really, really bad. Because if they aren't happening where we want them to, they're literally happening everywhere. That means you're making and breaking bonds pretty much at will inside your body. Right? That's like 1 second having 5 fingers, and the next second having only 1 finger because they've all now fused to each other. Okay? That's kind of a problem. That's a bit dramatic, but that's the idea. Okay? The product that is favored is the one that generates the more stable carbocation synthetically. Yes?
I thought if a reaction makes a strong acid, then it won't happen. So why is that one favored?
So what's happening here now becomes a little bit tricky. When we think about our strong acids, we're thinking about heterolytic bond cleavage. None of this is heterolytic. This is all homolytic. So yes, we are generating a strong acid, but if we also consider the concentration of said strong acid in comparison to the reactivity of our radical,
Very low.
yeah. Okay. The third act is now the complete death of the radical, termination. You start with a radical and you end with no radicals. The only way that happens is 2 radicals collide. Okay, that's the only way you can terminate it. Okay? Tons of different ways you can do it. We could have just had our radicals collide initially in any one of those situations. We could have even had 2 carbons radicals collide to make a larger carbon structure. Okay? The odds that those happen are really, really slim. Okay? They're slim because we're looking at relatively small concentrations of each of those radicals. Okay, so if I want to finish a reaction or run a radical reaction, I'll let it run for X amount of time, and then usually I'll take it out of the light and I'll throw something in to scavenge any unreacted radicals. That's what we're talking about here with the scavenger. So it's just a species that is now very stable as a radical so that when it bonds to the bromine, we quench the reactivity of the radical. This is why we have antioxidants. They're really radical scavengers. That's their whole point. Okay? How would we stabilize a radical? It's a permanent stabilization, not a bad idea. How could you stabilize a carbocation? Tertiary would be more stable than secondary, more stable than primary. How else could you stabilize a carbocation? With resonance. If you go up and look at now your antioxidants and look up those structures, guess what you'll find a whole crap ton of in those structures? Conjugated pi bonds, because they can do resonance to stabilize that radical. Okay? That's why they're antioxidants. Okay? So the utility. If I look at this reaction, I'm starting with an alkane. Right? Where's the polar bond? Maybe the weird face that I was just given there was because there isn't one. True. There isn't one. So how could I possibly go through to make that final product if I don't have anything to react? Okay. This is where radicals come in. I want to put or make reactions happen here. So just like we looked at with the previous propagations and all that, I can start with Br2, Br, and light. What happens? Well, the bromine splits, generates a radical. That radical will now find a hydrogen. Okay? that it can remove to generate a stable radical. Well, where would the most stable carbocation be in that structure? At the tertiary position, way up here at the top. Is there a hydrogen there? Yep, it was an implied hydrogen. Yep, you gotta watch out for them. Okay. What happens? You would now form the tertiary radical. That tertiary radical floats around in solution till eventually it encounters probably a second molecule of bromine. And I would end up with a new neutral product. That neutral product, does it have a polar bond? Yup. That is now this species. How can I move from the alkyl halide to the alkene? What do I have to do? What type of reaction? I have to run an elimination. What would help an elimination occur? A base. Okay? And in particular, a strong base. Okay? Give me an example of a strong base. Okay? NaOH, KOH. Okay? All of those would end up then generating that final product. Okay? If you can process through each of those pieces, you can start to come up with concepts. The radical may be tricky. Okay? So can I erase all that? The radical may be tricky. So start with something that shouldn't be tricky. The alkene. How do I end with an alkene? What reactions end with alkenes? Elimination reactions. Elimination reactions typically require what? Strong bases. I know information. It's a multiple choice test. Find an answer that includes a strong base, potentially an elimination reaction. Okay. That can help me work forwards. Maybe that gets me that I have this as a starting material. Okay. Even with the strong base and elimination, I know I need a leaving group. Put a leaving group on so that I can do that elimination. You now have that structure. How do you move between those two? Well, shit, I don't know. Okay. Is there anything on there that looks at like something I've seen before? Then that's probably not the right answer because I said I don't know how to do that. Cross that answer off. Okay? Makes sense? So you can think through these things. Use the test to your advantage. Okay? You are given that information. Whether they intended you to use it or not is irrelevant. Use it. Make sense? Okay. So our utility, ultimately they convert alkanes into alkyl halides. Super, super important. We can then get access to all the reactions that we've been talking about this semester. Okay, the reagents to do so. Bromine works great. So you'll see Br2 and light. Okay, that is a selective reagent. Meaning when I go through to run that reaction with Br2, I put the bromine at the most substituted position because that's the most stable carbocation. If I do it with chlorine, it also reacts. Awesome. But chlorine can't stabilize the radical as well as bromine. Why not? It's not as large. So because it can't stabilize the radical quite as well, it now becomes more reactive. So what is it going to react with? Everything it can. All hydrogens on that structure now go through to do radical substitutions, which means I get a crap ton of intermediates, or intermediate products. I'm going to get a ton of alkene products at the end. So chlorine, because it's not selective, is not a good reagent to choose for radical synthesis. That doesn't mean you don't see questions about it, okay? But ultimately it just means it's not useful for synthesis. Bromine is. Okay? Well, fluorine. Fluorine's even smaller than chlorine, which means if I form the fluorine radical, what's going to happen? It's going to react even faster than the chlorine. It reacts so much faster that pretty much fluorine in the presence of organic molecules causes explosions. Okay? It is insanely reactive. Iodine, much more stable than any of the above because it's big. So it is insanely selective. Okay? So much so that the reaction slows down to virtually a halt. Okay? So I want a reagent that now very carefully selects for the chemistry that I want, but then doesn't take too long to make that selection. That's bromine. Okay? Chlorine reacts, not selective. Fluorine blows up in my face. Iodine takes forever to get there. Okay? Which really means the only reagent we need to worry about when trying to react alkanes would be Br2. Okay? Kind of make sense? So your textbook has some nice pictures, though I think I borrowed these from someone else. Actually, those might be CARTI images. Okay, when we look at the bromine reaction, it is selective because it is an endothermic reaction. It's trying to form the most stable product. Okay? And so because of that, it becomes selective. Chlorine, on the other hand, is exothermic, in which case, like, hell if I care, I'm just going to produce products. Whatever those products are more stable than where I started, so it doesn't matter. I'm just going to go. Okay? Fluorine, if we drew fluorines on this one, okay, fluorine looks pretty much like this. And then probably somewhere down on the floor, we'd encounter our products for fluorine. It is that massively exothermic. What happens with iodine? Now somewhere above our ceiling, we have the products for iodine. Okay. Fantastic, great, we've got them, but I can't ever get there because the activation barrier is too high. Okay. Kind of makes sense? Okay. Stereochemistry and radical reactions. So if we ran this reaction, what would we get? Where's the most stable carbocation in that structure? 2 or 3. Okay, 2 or 3. They're ultimately the same, so it doesn't matter. So I'll just put the bromine there. Do I have stereochemistry or a stereocenter? Yes. Okay. So, which product do I get? Do I get the wedged one? Or do I get the dashed one? Oh, why do you say both?
That's what we've been doing so far.
We haven't been doing that so far. SN2 only got one. Remember, our radical acts like a carbocation. We have an empty p orbital where the bromine can dump electrons, either above or below. Okay? Ultimately, both answers are possible. We get enantiomers out of our radicals. Okay, so we will still get 2 products because we're still going through a pseudo carbocation intermediate. Okay? We could bring in optical activity, so our products would be optically inactive. Okay? So you might hear reference to achiral or racemic products as your end result. Okay? The next fun one. What about allylic chemistry? So here's our pi bond. What would you expect for a product? And not to be too leading or anything, remember we just talked about radicals. Where's the most stable carbocation? Okay. At our 2 position, so either here or over here, they're identical. So we might go through and say that our product for this reaction would be, right? Okay. Can be an enantiomeric, and it could happen at the other position and generates the same products, right? Everybody agree? Okay. So why the can? You could just say it's because of me leading. That's fine.
Exactly.
Okay, it's exactly the reason. Okay. Let's make a very subtle change to the reaction. What's the product? You didn't change anything. I did change something.
Go back.
What would have the second molecule of bromine?
What did I do?
Said addition.
Yep, that's how fast it goes. The presence of light is what will help you get the radical reaction. Now bromine splits into radicals. You get rid of the light, there's no reason for bromine to split into radicals, and it now goes through and does an addition reaction. That's a bit of a problem, because if I use bromine, I could very well expect two products. Okay? So how could I minimize that as an issue? We could make sure our reactions are all run in the dark. That gets a bit tedious. This is why we invented a new reagent. Yep. Heard someone actually already math it out. NBS. NBS produces minuscule amounts of bromine. The very tiny amount of bromine that is present, okay, prevents the addition reaction from happening because it's not present in a high enough concentration to do the addition. Okay? So that gives light an opportunity to split the bromine into radicals so that it can do the radical reaction. For those of you being like, but lab, shut up. Okay? And we can talk about that if you want in lab. This is what you need to remember. If I want to do the radical substitution, I will use NBS, and again, light is a big hint that this is tipping off. Okay? This will now do the radical substitution, okay, at the allylic position. Okay? If you don't want to remember allylic, just remember the most stable carbocation. Why is that position more stable?
Resonance.
Resonance. Okay? So NBS is a new reagent that will come in and kind of interfere with this and mess with things. Okay? That's ultimately what's happening down here. Shows the reaction. That's our structure for NBS. Those of you in lab that were wondering about why there was a carbonyl in your spectra, there it is. Okay, so our radical substitution reagents. Notice in all these cases, we did a substitution. We traded traded a hydrogen for bromine. Okay? So Br2 in light, awesome. Cl2 in light, not so awesome. NBS in light or heat, okay, gets us a bromine substitution at an allylic or benzylic position. Okay? The only reason we would use NBS is because we're just trying to avoid the contamination with the addition reaction. Okay? If it's just an alkane, we'll just go straight to bromine. There's no need to move into NBS. Okay? Kind of makes sense? So really, two reagents. That's it. Br2, NBS. That's what you need to remember. And you need to remember that those do radical substitution. 5 minutes and like 2 or 3 slides. Not too bad. Radical additions. We will also see radical additions. Remember we talked about ROR, or mentioned ROR? We haven't seen that yet. Here's where ROR comes in. Right? I start with an alkene, HBr, and ROR. Right? ROR goes through in the presence of either light or heat, and it catalytically splits into the radical. I now have my radical that is reactive. What is the most likely thing that that radical will encounter? Why hydrogen? Which hydrogen? Nice. Okay. Remember, we're trying to generate the most stable product possible. What atom can stabilize our radical best? Bromine, which means more than likely our radical encounters the hydrogen from HBr. I then form carboxylic acid. Meh, who cares? But now I have a bromine radical. Now I can initiate the selective radical reaction with my alkene. What's the most reactive thing in the alkene? The pi bond. So now what happens? The pi electrons come out. Okay? One of those pi electrons goes to form a bond with the bromine. Where does the other pi electron go? to one of the carbons? Carbon 1 or carbon 2? Or why not? Or carbon 3? Can it go to carbon 3? No. Carbon 1 or carbon 2? Okay, probably 2. Why 2? That would generate the more stable carbocation. There's my bromine. There's my radical. What's the most likely thing for this molecule to now encounter? Another bromine? What's the amount of bromine that I've produced? I've got a single molecule of bromine floating around as a radical. What just happened to it? I just killed it. Okay? There's a possibility for another roar. Roar is added in a catalytic amount, meaning a very tiny amount. What is the most likely thing this radical will encounter?
Another one of itself.
More HBr. HBr is present in that solution in a very high concentration. What happens? It picks up the hydrogen, and I end up with this as a product, and now more bromine radical, which can now go out and do the reaction again. Okay, let's call attention to the addition reaction we ran. What did we add across our double bond? Actually, before we answer that question, can I erase? Okay, beginning to end, right? What did I add? I added a bromine and a hydrogen. So I added HBr. What charge is hydrogen? Positive. What charge is bromine? Negative. If I look at the starting alkene, I have carbon 1, carbon 2, and carbon 3. What charge is carbon 1? Most likely to be. Partially negative. Why? It would be more stable with the electrons outside the structure. The other one's partially positive. If I looked at just adding HBr, where should the hydrogen go? Position 1. Where should the bromine go? Position 2. What was the result? It did the opposite of what I would expect. Right? So when you do an addition reaction, it does the opposite of what you expect. Okay? There's two reagents you should be thinking of. Boron and radicals. Those are the only two that are going to do the opposite of what you expect. For those of you being like, oh, well, now I got to memorize anti-Markovnikov. Remember how I said anti-Markovnikov isn't relevant? If we go back through and look at our reaction, oh my gosh, that's really far back. Jiminy Christmas. I didn't actually erase it. There it is. If I look at the reaction and evaluate stability all the way through by looking at, heaven forbid, electrons, is the chemistry any different than anything we've talked about? No. It's all about stability. There is no Markovnikov, anti-Markovnikov. The reaction of where those pieces went was dictated based off of the chemistry of the molecules. Okay? This is why focusing on the chemistry becomes important and not memorizing some silly rule. Okay? Yes, that's a lot of work. I apologize. Okay? So, radical additions, we got a bunch of steps to go through and show that. Come on, get me. Our Birch reduction, we saw that one with our transalkene. That's also a radical. Where's the slide I wanted? So our addition radicals, we've got that. We'll encounter this one largely in second semester. What makes this one trickier than what we did with the HBr? We got roar. What does the roar react with? Is there HBr? No. So what does it have to react with? The pi bond. It generates a radical. What is that radical likely to encounter? Another pi bond, which would mean we generate another radical, which would interact with another pi bond, which means another radical. When does it end? It doesn't. Okay, what we end up forming is what's known as a polymer. Okay, so you'd be looking at polymer chemistry. You can still see those results. Polymer chemistry takes up an entirely own field. You can take an entire class on just polymer chemistry and barely scrape the surface. And for whatever reason, we've decided it's important enough to throw it into OChem to make you go, oh, there's more stuff that I don't know. Yes, sorry, but what you're looking for is trying to find those repeating patterns. Okay? The big thing that I wanted was really this slide, because this slide shows our reaction summary for our radicals. If we have alkanes, we've got bromine and chlorine. For alkenes, okay, we have NBS, which gets us our, what's the word? Radical substitution. We have bromine, which would do an addition, which isn't radical, okay, or HBr, getting us our anti-Markovnikov addition. Okay? So that slide really summarizes everything that you would need within your radical reactions. I'll come back to it. I'm just curious to see what this slide is. Yeah, don't worry about it. Is there more? Oh, seriously? Gosh. Okay. Conjugated pi systems, we've already talked about those outside of the context of radicals. Right? It also Diels-Alder has a conjugated pi system. That's why there's that online video that you are responsible for watching.